middle between the two vertical asymptotes, aka the point that it's going to go through as it goes down. Okay. So here we are, back at our cotangent example. People just joining us, Lo siento, we forgot the work to video record our first few steps. We've just found the period, the first vertical asymptote, the first point of inflection, and talked about plugging into our formulas up above. Okay. Whew. Do we start with the period? No. I'm just going to answer it. No. We start with the stuff we can put in the graph. Okay? So, first vertical asymptote at 0. But yeah, literally they're like,
Sounds bad
maybe they're excited because it's up. Maybe they cut down the palm tree to get it up. So, okay, come back.
Yeah, sounds like
Partially, just 2 branches. Okay. Oh. Yeah, I'm kidding. That's our first vertical asymptote. Where's our next vertical asymptote? 3 pi away because of the period. To find the next, so maybe we should count by 1 a pi, 2 a pi, a 3 a pi, right? Could we go backwards too? 1 a pi, 2 a pi, 3 a pi? Now, technically, we have a point that we're supposed to graph. But Jason brought up a good point. He said, isn't that just halfway in between? Yeah, it always will be. So if you have this, and if you have this, where would halfway be? Go 1, and go. Isn't that the same thing as 1/2 of 3 pi? Or 1.5 pi, 1.5 pi? And what would happen if we're going back here? Halfway in between. Guys, this halfway in between trick works for tangent too. You can find the vertical asymptotes halfway in between. You got the point. Unless there's a d that moves it upwards. So then halfway in between, it's negative 1.5 again, which is also 1, 2, 3 pi away. Then all you have to remember, don't stress about the number. I mean, a normal cotangent is like this-ish. If there's a 2 or a 3 or a 4, it starts to become more and more like a line. If there's like a 1/2, 1/3, it starts to become flatter and flatter and flatter and flatter. So, okay, we can make it kind of more like a line. Are they alive?
Huh?
Are they alive?
We got to take it out. The whole thing ripped off. Except for
Sorry guys, we tried.
We won.
Next year.
you should have like a pity vote.
Okay, so then coming back.
Who was laughing? It was a bad
It was a good idea. When it's all taped on, yeah, with the wind. Hold on, cotangent. I know, everyone, I know, but I already said we need to focus because we need to, okay, stop. Cotangent goes where?
Down.
Down. So we need to be kind of spread out because the 2. But don't stress too much. As long as you have it going down, I'll probably be fine. As long as your vertical asymptotes are there, your point is there, we're good. Going down, going down. Soft cousins class are probably like, anyway. Couple seniors. The juniors, we do love you, and it was a cool design, and hopefully the judges still kind of see where it was. They were the office ladies, they saw it this morning. Good. How close is cotangent and tangent? Pretty close. What switches? These formulas. And tangent always goes up. Cotangent always goes. Now, are the formulas important? If you have a highlighter, if you're like a colored pen kind of person or a highlighter kind of person, I would maybe just take a second and highlight for tangent and cotangent the sets of formulas. They're really stinking important, right? Not a bad idea for tangent and cotangent. Formulas are really stinking important. Question. For sine and cosine and all those, what's important for sine and cosine?
The formula, the changing it.
Yeah, the formula with all the changes in it. And do you remember what that formula is?
It was D plus A sine cos.
Yeah, it's whichever one is there, right?
B X.
Right? Sinusoidal axis, amplitude, the different shapes. Sine starts in the center, right? Cosine starts at the top, unless there's a negative and it flips. This one is your starting point, your phase shift. This one you use, what's the period formula for sine or cosine?
2 pi over
Yeah.
b.
1 over b times 2 pi, or you could think about it as 2 pi over b. This is the key to sine or cosine and understanding it, and these are the key for tangent and cotangent. How many graphs do we have?
4 more.
All we need is 2 more.
Oh, no.
Do you remember? No. Do you remember what I showed you yesterday?
Say again?
Or can you see
I did it up here.
Oh, yeah, the bounce.
Oh, I said we only have 2 more trig functions.
Oh, I got it.
Because sine, cosine, tangent, cotangent, we have 2 more, and that'll finish the section and finish all of our trig graphs. Okay? So, yesterday, didn't I graph a sine, but I made it dotted? Do you remember what I did next? I bounced. Yeah? Okay, so here we go. Secant and cosecant are last 2. And if you notice, wait, doesn't this look a whole lot like the sine and cosine?
Exactly.
Because yesterday I said, and even the day before I said, if you're really good at the sine or cosine, you got the cosecant, secant. You just got to kind of learn the couple tricks to get it. But you start with a sine or cosine.
Welcome back, Becca.
She was helping juniors with their work. Now she's trying to get mine. Okay. We're gonna start, you guys are ready, keep going. I'm not gonna start anything crazy, I'm just gonna say, graph. Go ahead and take a second, get the notes down.
It died.
Yeah, like hardcore died.
Thank you guys for trying.
Really sad.
Falling off the board guy.
You have to take it apart.
I could build a sandcastle with the dirt in my eye.
Yeah. True, it was bad.
Thank you everyone who went out to help. I appreciate your class, thanks you too. But maybe by sparkle tonight, maybe like during lunch after school, you guys can get back up. I
Oh,
bet
if
if you.
the paper's torn,
I can't see.
you can't put
dirt in
the
my
hinges won't,
These
yeah.
think duct tape's for.
Tyler, we tried staples,
It's
box,
okay,
and
it's
tape.
okay, we got it.
There's like a lot of dirt.
I know, right?
I can't see.
Because it was just like flying.
Yes.
Windy.
Okay, the juniors, just from all of us, we saw it, it was a really cool one.
Yeah.
Alright. What? Wait. I love you guys, and the board thing was super important, and it was really, really cool, and I'm super, super sad for you. I don't want your breakout grade, think because of it, okay? What did I write?
Sine instead of cosine.
Wait, what? Cosecant isn't sine, but what is cosecant?
It's like a negative
1
2, what did it be?
over sine. No, don't go put negative. Don't go put negatives in. But cosecant is, who is the reciprocal of? Sine, right? So the reciprocal of cosecant is sine, or cosecant is 1 over sine. Now some of you are like, well, why isn't there a 1 over? Just trust me. To graph it, we need to start with his reciprocal function, sine. And here's the great thing, graph it. But I'm going to put a little dotted line in front. Do you guys know your graphing calculators? Before the equal sign, there's like the dotted line, the solid line, the shading below, the little circles, they can change it. That's what I'm telling you, make this dotted, okay? All right, how do we graph sine? We get to review, let's go team. How do we graph sine?
Starts at 0.
Starts at 0 because that's our sinusoidal axis, right? Let's pretend that's 0.
The
Oh,
get
well,
2.
that didn't work anyway. Try again, take 2. D equals 2, means what? 0. T equals 0, y equals 0, that's our middle. Now what do we do with the 2? It's called our amplitude.
Yeah. Go up to.
Up to,
Yeah.
down to. We are upper bound and our lower bound. Okay, cool, so far? We got our D, we got our amplitude, up to, down to, we got our middle of 0. Sine, what does he look like? Right? Starts in the center. Ooh, the only way he'll be different is if there's a negative and then we'll flip him, but he's not a negative. Okay. There is technically a B that we could do next. I kind of like to figure out the starting point first. So let me just keep with the system that I've been showing you. From this number, we can say our starting or our initial point is x equals, careful,
Negative.
y negative, because it's x minus, right?
Oh,
It's x minus. So when there's a plus, oh, there must have been a negative number in there, right?
Yep.
Negative pi over 4. Don't go graphing anything on the x-axis or on the sinusoidal axis until we find the period. So then what's the period? We wrote it up there.
Or B.
Yeah, and since b is 1, does it change anything? No. Okay, cool. Now one more thing that might help us. One more thing that might help us is the quarter cycle. Some of you are still kind of like, why do we do that again? Remember, every quarter of the graph, there's a new go forth, go forth, go forth, go forth. There's a new key point. It helps us know how much to count over to space everything perfectly. So our quarter cycle says take the 2 pi. Quarter cycle says multiply by a fourth. 2 pi over 4 is pi over 2. Which, you see this yucky pi over 4, dude? Maybe it'd be helpful if we got them in similar or like terms, which means another way of looking at pi over 2 is to make it 2 pi over 4 times 2 over 2. Times 2 over 2. Okay. I'm going to count by pi over 4 is y, because I have to start at pi over 4 to the left. So I'm going to make little tick marks. I'm going to go negative pi over 4. And I need enough to fit in 2 pi. That's 8 pi over 4. I need to fit in 8 of these. So we have 1, 2, 3, 4, 5, 6, 7, 8. Another way of looking at it is we multiply by 4 over 4. Try to put everything in terms of fourths, because those are my tick marks. And technically, if you guys are looking at this, you're probably like, she didn't do a good job, right? Fine. Is that better? Okay. So sine starts in the center. How far do I move to get the top? Remember,
Order.
middle, top, middle, bottom, middle. I move 1 tick mark or 2?
2.
I have to go 8 altogether. I only get to take 4 steps. I need to go by 2s. So I'm going to go 1, 2, 1, 2, 1, 2, 1, 2. Now, if this was just sine, what would I do?
You're done.
Connect it. I'm done. Draw little arrows. Ta-da! Ugh, but what is this?
Gosh darn it.
Cosecant. Now, I am going to connect it, but what am I going to connect it with? Now, I haven't made this perfect. I'm just trying to show a point. So I'm including more of it. We could count tick marks and count 8 back. Just trying to prove a point. Now, guys, here's the struggle. We needed that. This is the most important step for getting cosecant, but there is something you have to realize. This is good, but it just forms, in a sense, the handwriting lines for cosecant, secant. What do I mean handwriting lines? For sine and cosine, what were we finding to help us guide where to put our graph? Right? Talk about elementary school and how you guys would deal with the little a, the big A, all that stuff, yeah? This was good for sine, cosine. We had to figure out our initial point and put it. But we need all of this for cosecant. But look, now it's easy. Because we graph our reciprocal first, we join at all the maxes or mins. Dotted means this isn't the cosecant graph. This is the cosecant graph. Okay? We join at all the maxes and mins. So go ahead, put big old points at all the maxes or mins. And there would be infinitely many, we only do a few, right? We join at all the maxes or mins. They have the same highs and lows. Well, kind of, you'll see in a second. We go to each of the intersections with the sinusoidal axis and we make vertical asymptotes. Because the intersections are the zeros of the original, which means they're the 1 over zeros for the reciprocal, cosecant or secant, whichever one we're doing, cosecant in this case. We join at the maxes or mins. We make vertical asymptotes at the intersections, and then we bounce. We bounce. We have to stay within the vertical asymptotes, and we hit at the max or the min. Now, his max was his min, but either way, they share a point. What are we going to do to keep going? We bounce. And we bounce. If you guys want to double check and make sure we're right, which we are, but you can get out your calculator and see if you can graph. Remember, sometimes you get to use your calculator. See if you can graph a function. This function. Now, there's a couple things I want to show you in your calculators too. Go ahead and grab them out. Kiddos, if we have a pi over 4 as our initial angle, what mode are we in? Good, good. If we have pi over 4, we're in radians, not degrees, right? That would be 45 degrees. That doesn't work. Wait for it. Wait for it some more. Okay. How would we graph cosecant? Good. Well, technically, can we do 2 over since there's a 2 in front? We'll do 2 over because it's in front. But we are having to do over because there's no cosecant button. Don't you dare go to those little -1 buttons. Those are not cosecant or secant. You have to go 1 over 1 divided by who? Sine of x plus pi over 4. We can do Zoom Standard. If you want to use that cool Zoom Triggy one from yesterday, that might work as well. Oh my goodness, look at that. Bounce, 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 bounce. Now kiddos, here's the dealio. I could have you memorize brand new clues for cosecant. And I could have you memorize where each of these points are. And have you memorize their vertical asymptotes. But what do you already know that fits in between that you can graph and get everything from? Sine or cosine. In this one, cosecant, sine. You just need to know the trick of every time it passes through the sinusoidal axis, we make a vertical asymptote. That's what holds these graphs in the sense of how narrow they are or how wide they are. And we join at the maxes or mins. Some of you are like, I like memorizing. All right, cool. I guess I could give you, if you want to come in during lunch after school, I can give you stuff to memorize to be able to go straight to the graph. But if you're like, I know how to do sine or cosine, why worry and memorize more? Okay. You just need to think of join the max or mins, bounce, but make vertical asymptotes at all the intercepts. Yeah? Does it kind of make sense how the two tie together? Sine with cosecant? Guess what happens with secant and cosine? Same thing. Graph the cosine, make it dotted. Intercepts are vertical asymptotes, join the maxes, mins, bounce, 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 bounce. Bounce, 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 bounce. There you go. There you go. So guess what? We made it. But since you have your calculators, can I show you one more thing real quick? It's going to come with your homework. It won't be on a test or quiz. You'll never have to do it by hand in here. But it's cool, because remember how we talked about the pebble in the water? And then the ripples being sinusoids? But we said, wait a minute, hold on. The water eventually becomes what? Still. Well, what we're graphing goes on how long? Forever. That's not practical. So if only there was something that could make the sinusoid decrease, getting closer and closer to zero, like the stillness in the water, right? Okay, there is something, and this is how it works. You can dampen, oh, is there like dampening sound? To dampen? Or a damper, or, whatever. To dampen, like to decrease, kind of, okay? We can have damped trig functions when you multiply by something else. When you multiply the sine or the cosine by another function. I'm gonna write this one big because I don't know, you can see the graph well, but the functions are kind of little, so let me show you what the functions are. Is there a sine in that function? Yeah. But what else is in there? What's being multiplied by sine? X. If we were to take the sine away for a second, what does the x look like? Y equals x? Isn't that this line right here? And guess what? Because it's being multiplied by sine, sine is sometimes positive, sine is sometimes negative, which means not only are you going to graph y equals x, you're also going to graph y equals negative x, hence the reflection. And if you graph both, what do you notice about the sine? Sine starts in the center, no transformations, starts in the center. What's the sine being held within? Those two lines. So it is a sine, right? But what's different? What's being multiplied by x, which means it kind of has these restrictions, which actually is making this one grow. So even though we're calling it a damped function, it's actually amplifying it, right? Making it grow and grow and grow and grow. Now some of you are like, okay, this is weird. Sine should go down. Normal sine would. But when you have times x, it's actually going to be a horizontal reflection. So it's not behaving like normal sine in the sense of going up to the right and down to the left. It's actually copying the other side. Now you're like, well, that doesn't look like a ripple in a pond. Okay, all right, fine. What about this one? We're not going to go to our calculators. You can graph it in your calculators if you want. But e to the x, does anyone remember what e, I know it's e to the negative x, but what does e to the x look like? Remember?
What?
Exponential growth? Yeah, he grows, right? ln goes this way, e goes this way. So, if it's e to the negative x, it's e to the x but flipped. So if e to the x is like this way, then what would e to the negative x look like? This way. So e to the negative x, if I have him coming in like this, and to be honest, kiddos, your grapher, you'd have to make the window really funky in order to be able to see this because e to the x grows so fast. So I'm not having you go there because the windows you have to play with and you have to work on it for a while. But what you have here, wait a minute, I'm supposed to make him what? Dotted, right? So let's go ahead and reflect him down here. Roughly. Sine starts in the center. Let's say the pebble gets dropped over here somewhere. Yeah, over here it's growing, but what happens as time passes? Is that a little more real life-ish? It's going to eventually. And thus, where we started in these sections of graphing 5, 4, 6, with the pebble dropping in the pond and being like, what, that's impossible. We now get to end and say, oh, we can model that. We just need to go ahead and restrict or dampen the sine function. Yeah? Okay. Some of you guys are graphing to try to see it. You might have to change your windows. Long story short, you need to include tons and tons of y's. So maybe go up to like 1,000 and negative 1,000 for your ymin, ymax. X's, maybe keep them kind of small still, negative 10 to 10. See if that would work. That'd just be a guess right off the top of my head. All right, we're going to 4-7. But, what could you have been, should you have been, can you definitely be doing this weekend?
Homework.
What's due on Monday?
Homework.
4-6. What could you have been doing last night on it? half of it, cotangents and tangents, but we got to review those today, so maybe you're more ready now, if you didn't feel ready last night. And now you have cosecants and secants, which come from, help me out.
Sine and cosine.
Come from sines and cosines.
Wait, so 4, 5, we graded yesterday.
Yeah.
4, 6, when
We're
graded
grading on
Monday.
Monday.
Okay.
Because we could grade now, but I think we reviewed tangent by doing cotangent. And we did an example of cosecant, which is just like secant. So I think instead of going to homework and seeing where you got stuck, I'd rather you go back to homework and then try again now that you've seen more examples of all of them. Cool? Cool. All right, 4-7. 4-7. Kiddos, right now in your homework sheet, I have 4-7 as two separate homeworks, 4-7 part 1 and 4-7 part 2. Today, before class is over, so before 2:45, I'm going to go ahead and condense those homeworks in one and shorten it. Sound good? Okay. I'm going to condense, because technically we should have part 1 due on Monday. I'm going to go ahead and shorten it, condense them into one homework, and then have it due on Tuesday. Cool?
Yay.
So I just want to give you guys a heads up on that. At this point, there are 2 more sections in chapter 4 that we're trying to get through before the end of the semester. 4-8, I already told you, could be a huge section. We're just spending like half a day, maybe a whole day, but we're shortening that one intensely as well. So that homework's going to change a little bit. So for those of you guys that print out your homework sheets early, 4-7 and 4-8, it's getting shortened and condensed. By the end of the day, I'll make sure that's done. So we're kind of just seeing overviews. Then we'll come back after the semester break. We'll probably have to review a few of these things, but we're going to have sections that'll help us review them because we're going to be using this stuff. I just want to give you an introduction before we're done. 4-7. I need to show you something before the weekend because I need you guys doing one other thing this weekend. Maybe not 4-7 homework. I need you doing something. So let's get a little bit of notes and I'll show you what I need you to be doing, okay? Inverse sine. Okay, well, how did we ever invert functions? We start with the original one. Start in the center. There we go. We start with the original one. That's sine, right? Why? It starts in the middle or in the center. So there's sine. Okay. How are inverses seen graphically? How are inverses seen graphically? Reflect over, do you remember what? The y equals x line. So we could graph the y equals x line. I think some of your homework actually has you like graph the y equals x with a function so you can see it. And we would think, now this is a little crazy, remember sometimes reflections are hard. See this one on top? Where's it going to go?
Down.
On bottom. See this one on bottom? Where's it going to go? On top. And then, can you kind of see how it's going to start?
Oh. Oh, God.
Right?
Oh,
Instead of going around the x, where's he going around?
why?
The y. Yeah? Instead of going around the x, he's going around the y. Get some prominence out of that one. But anyway, coming back. No. Oh. Yes. Instead of going around the x, he's going to, remember, instead of being on top, he's on bottom, he's going to go around the y. Does that make sense? Now, the units are a little different because the angles we go by pies and radians, and the other ones we go by 1. So it might not look quite as perfect in your calculator, but that's the idea. Jason?
So he's flipping and turning?
He's flipping.
Yeah.
So, I mean, it turns it, it's really just flipping. Does that kind of make sense? We can think of it as turning, yes. Yeah, yes. Think the x's and y's switch. So instead of going around the x, it goes around the y. Okay. The problem is, can you guys read for me the title? I know it's up above, but what's the title?
Inverse true functions.
Why is this bad?
Because it's
Oh, the function. Because the function needs to pass what?
oh, the horizontal vertex. Vertical.
The original has to pass the horizontal so that his inverse will pass the vertical. Does that one pass the vertical? So there's this special thing called restrictions that we need to put in. Restrictions that we need to put in. Where we need to cut the graph to get the inverse. Now guys, if we had time, and we don't, If we had time, I would have you go to your calculator and graph this. How do you make this? How do you put this in your calculator? Second sign, not cosecant. It's not bouncing off of anybody, right? Not cosecant. Second sign. And guess what it's going to show you? The cool little snaky thing? No. It's going to show you this little piece. Why? This is the part that's a function. Okay? I know, it's kind of lame, it's not as cool, but it is what it is. So here's the idea. The graph of inverse sine literally is this little puppy right here. And if I was to show it to you, if we were to label everything and flip everything, long story short, everything kind of, well not kind of, literally flips. The domains and ranges flip, just like inverses always do. So everything is a little bit backwards, and it's not as long as normal sine. So we have a domain, you guys remember this part, how left, how right. You might not know this one yet, but how left, how right. That's going to be
-1 to 1.
-1 to 1. How right,
Negative,
oh, sorry, range. I saw R and I said right. Range,
negative,
how low, how high?
negative half pi to half pi.
Yeah. Negative half pi, or we shortcut it pi over 2, to positive half pi, or pi over 2. Okay. And if we were to need to solve a sine inverse, let me put a quick example. Need to solve a sine inverse function. Okay, back up so you can see. Y equals sine inverse of x. If we're plugging in 1/2 sine inverse of 1/2, here's the crazy thing. Why is there a 1/2 of sine? Usually we have sine of pi over 3, pi over 6, maybe 30 degrees, 45 degrees. Why is there a 1/2, and what on earth does that? Everything is So you used to say, or I used to give you unit circle quiz, sine of pi over 6 is, or sine of 30 degrees is, and you guys would tell me? Oh, good.
Wait, what'd you say?
Sine of pi over 6, or sine of 30
Sine
Is 1/2.
is 1/2.
I don't know.
Sine of pi over
My
6,
brain's
this is
all-
what I would have put on a unit circle quiz, right? Or I could have. Sine of pi over 6, and you would have told me, hopefully figured out, 1/2, cosine root 3 over 2. But what is sine inverse gonna do?
Flip it.
The x's and y's flip. So over here, when I write down sine inverse of 1/2, you have to know the unit circle so well that you're like, when is sine 1/2 at
Pi over 6.
pi over 6?
Or nothing.
I don't like this.
I agree with Ricky.
Do you at least see what I'm saying, even if you don't have it memorized good enough to get it yourself yet?
But what?
Before, sine of pi over 6 is 1/2. Now you'll just see sine inverse of 1/2, and you're like, in a unit circle, wait. If you were to literally get out your unit circle, you would see a little y value of 1/2 at pi over 6. But actually, does anybody know it so well they actually know there's another place where it's 1/2? Not the negative, careful, that's negative 1/2. Where else is it positive 1/2? Sine is positive, all students in the first and second quadrants. Oh, well stink, there's more than one answer? We should sue. We're only supposed to get one answer in math. Well, we know it's not always true, but
We should sue.
we still like only getting one answer. And to be honest, the function part, the restriction part helps us just to get one answer. Because what do these restrictions say? Only, for sine inverse, only look where? Up, pi over 2, and down, pi over 2. So if we're only allowed to look between negative pi over 2 and pi over 2, up 90, down 90, are we even looking in either of those two quadrants? No. We're only looking here or here. So if I was to give you something like y equals sine inverse of negative root 3 over 2.
30, 60.
we're only looking in these two quadrants, up pi over 2. So don't the answers, these are where we're allowed to look only. Down pi over 2, forget those. Will this answer be in the first quadrant if the sign value is negative? No. Okay, 30-60 or 45? 30-60, okay, which one?
60.
60. You know why?
Because 30 was
Because the
one.
y is longer? Or some of you might have to go to your table and say, oh yeah, sine is root 3 over 2. 1, 2, 3, oh, that's 60. What is this? Oh, hey, this is 5 pi over 3. Dun, 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 dun. That's not allowed. You have to go this way. Aww. How could we get there going the legal way?
Negative.
Negative. Wait, why was I super purposeful that, well, A, we have to get stuff done, B, we were distracted, but C, what do you have to know really well
unit
to be
circle.
able to go backwards? The unit circle. So cool kids might not like it, but it's necessary. This weekend, wait, focus, eyes on me, hands stop. As soon as hands are moving or mouths are moving, I lose half the class. Okay, backboard. I didn't even put a due date for 4-7. Don't stress about 4-7. We'll get to 4-7 when we get there. I'm shortening it and combining it. Homework for Monday. Finish for 6. What are you working on? Trying to get down. How to graph cotan, tan, cosecant, secant. Reviewing sine, cosine to get those two. But what's the other huge thing you should be working on?
Final.
Unit circle. Unit circle, which will be on the final. It's chapter 4A. It's still important it's reviewing, but what's it going to help you tons with?
This.
Get out of here, cool kids. Happy Friday. Hope you see the sparkles. Don't come if you don't have a jacket. Get a jacket. Thank God. Take your vitamins. Stay healthy.
No, it's
Don't
fine.
sneeze on people.
I've
Watch
blinked
your
them out.
Alligator. Stay healthy, okay?
Yeah.
Not that it's really your choice, but.
I'll do my best. Did I leave anything?
You have
I'm
your phone,
leaving
right?
those cookies.
Okay.
I didn't bring anything to school today.
What about you? Important part.